Hey, welcome everyone, and thank you for joining our session. I'm Janie Page from Lawrence Berkeley National Lab, and it's my great pleasure to introduce Jessica Granderson, who is a staff scientist and the Deputy of Research Programs for the Building Technology and Urban Systems Division at LB&L. So in that role, she works with Marianne Piet and helps guide what research we get into. She's a member of the whole Building Systems Department at LB&L. She holds a PhD in mechanical engineering from UC Berkeley and a bachelor's in mechanical engineering from Harvard University. Her research focuses on building energy performance, monitoring and diagnostics, advanced measurement and verification, and intelligent lighting controls. In 2015, she was the recipient of a Clean Energy Education and Empowerment Award for leadership in research. So with that, I hand it over to you, Jessica.
Thanks, Janie, and thanks everyone for having me this afternoon. I'm going to talk about energy management and information systems, starting with a bit of grounding context. It's the case today that the data revolution has hit buildings in the same way that it has many other industries, and that's driving a real surge in new solutions for both building control as well as analytics. And whether we're talking about researchers or product developers, we're all thinking about and exploring how machine learning, Internet of Things, cloud computing can converge to transform our building operations. And that's driving a more nuanced need to understand how users are actually benefiting from new technologies, what their as operated costs are, and further development opportunities to advance existing technology in terms of its usability, its scalability, and its overall performance. So in today's talk, I'm going to cover the state of the art in what's available off the shelf today for commercial building, energy analytics and control software. I'll share recent results from documenting their as installed costs, savings, and how people are making best practice use of the tools. And then I'll end with some highlights on new research that we're conducting at Berkeley Lab to expand today's capabilities through using novel data sources. So today's state of the art, we refer to a broad class of technologies as energy management and information systems. What these do is ingest data from a wide variety of sources, be it utility bills, smart meters, weather, data from building control and automation systems, and so on. That data is centralized into a common warehouse and then served up for analytical and control purposes. And we like to think about the capabilities of energy information systems to analyze that smart meter interval data at the whole building and portfolio level, fault diagnostics to analyze control system data and identify operational problems and equipment failures or component failures. And a third class called automated system optimization that looks at predictive control for HVAC systems. So here's a few screenshots of those capability classes, starting on the upper left with fault detection and diagnostics. So these are whole suites of algorithms continuously analyzing control system data, identifying problems with either the control logic itself or with the mechanical equipment and components. So what you see here is every row and every line representing a fault and the color coding indicating its presence or absence in the operation of the system. Moving clockwise, the HVAC predictive optimization technologies relative to the others, more emergent in today's market. These are looking at day ahead predictions of load or building occupancy and constantly adjusting control parameters beyond what you might otherwise find in the static programmed sequences of operation. On the bottom, I'm showing energy information systems. These are the smart meter analytics technologies telling us how much energy is being consumed at what time of the day, and through sub-metering in what pieces of equipment or what areas of the building. This allows us to identify instances of building energy waste. 2 points I want to make about this technology and how it differs from other smart building technologies or efficient building equipment. And the first is that these are very much human in the loop process tools. So to gain any benefit, the user, the building engineer or the operator has to actually take the findings that are surfaced through the technology and translate that into some action to either resolve problems or make efficiency improvements. That's true really even in the cases of the automated HVAC optimization capabilities. You're still never really taking the operator completely out of the loop, nor is that the intent or the objective. Second is the real continuous nature of use of the technology. You can kind of see that in the circular flow in this diagram. We're really talking about an ongoing process to continuously monitor for opportunities or problems, fix them, and then track performance to ensure that savings are maximized and that they persist over time. So what we used to be able to say about this technology is that there was very compelling savings potential, anywhere from say 5 or 15% of whole building energy use savings resulting from their use. And that was across a wide body of case studies. A lot of those studies were generated by the technology providers and vendors themselves, and they would use different methodologies, different metrics, and that made it really tough to synthesize across findings or really generalize and say, what do users save on average? And unlike hardware, there was really no information in the public domain about what does this stuff cost. You would have to go start your way down the path of procurement and discussion with the vendor to even get any notion of cost. So that all added up to under adoption of the technology, really driven by uncertainty in the business case and the value proposition. So with that kind of base level of understanding as our foundation, our team worked with 104 portfolio or campus scale organizations to conduct the most comprehensive study to date on the costs and benefits of EMIS technology. Our study scope covered over 500 million square feet of technology install space, 6,500 buildings, and our participants and partners in this work were using some 40 different off-the-shelf analytics and diagnostic technologies. What we found was significant portfolio scale whole building savings subsequent to installation of the technology. Folks who were using the meter analytics tools or energy information systems on average saving about 3%. Those using the dedicated HVAC fault diagnostics, a full 9% whole building portfolio wide savings that translated into median utility cost savings of $3 million a year for these organizations, with a 2-year payback based on first year costs of anywhere from a couple to just under 10 cents a square foot. So one thing that we wanted to get from this study was to understand what are the benefits of these technologies. And I'm showing some of those results in this slide. First, and quite obviously or intuitively, energy savings and associated utility cost savings. Beyond that, and that's really driven through, I'll talk about in the next slide, very much operational, no cost, low cost types of measures. So it was interesting to learn that some 80% of our technology users in this study indicated that there was significant value of the data to inform capital improvements, retrofit strategies, and the data that could also be used to validate those project level savings. Some non-energy benefits also mentioned more than half of the time: improved occupant comfort and operations and maintenance staff labor savings due to streamlined operations. So we talked about, and we found, either 3 to 9% portfolio-wide savings following installation of the technology. And it's important to understand precisely where are those savings coming from. What are the insights that were gained through use of the technologies? What we found, definitely that the technologies are identifying scheduling opportunities. That could be overrides, lockouts, or making improvements to existing schedules so that they better align with the actual as used occupancy patterns of the building. A whole other series of measures, all associated with set points and reset schedules. So that could be overnight and weekend low occupancy setbacks. That could be making sure that supply air temperature and duct static pressures resets are working right at the air handler level, all the way up to chilled and hot water supply temperature resets at the central plant level. That's really the kind of core of the most commonly identified issues that are translating into these material savings with rapid payback. The other major contribution of this work was to finally be able to say something comprehensive about technology costs. In the first couple rows of this table, I'm showing costs for interval meter analytics technologies. And in the next block, I'm showing the fault detection and diagnostic class of tools. We were able to break savings out into the upfront configuration and installation one-time component, as well as the recurring annual component. And based on the data that we obtained, we could normalize costs either on a square footage basis, that's the rightmost column in the table, per building, or even per data point that was being ingested for continuous analysis. The meter analytics technologies, we can focus on cost per square foot, about a penny. Now, these are very large installations with the average of 1 to 5 million square feet. So you wouldn't necessarily extrapolate this into, single building sites. $1 penny a square foot upfront, as well as recurring. Now, when you move into the fault diagnostic class, you're now incurring more upfront cost. And this is really driven by the need to integrate the data going into the building automation and control system, more complexity there, and just a far greater volume of data that's being ingested and interpreted. By the time you look at the recurring annual costs, however, of those technologies, you're back down to pennies a square foot. So in spite of the differences there, both of these classes of tools were giving us a payback and return on our investment on average of 2 years. So far, I've talked about medians across this cohort of over 100 organizations and usage in thousands of buildings. It's really important to recognize that there's a lot of diversity in the benefits that people were able to achieve. So there's a wide distribution in the savings that resulted, and we wanted to extract an understanding of what the best practices really were from those who were deriving maximum benefit. And first was around organizational process and making sure that use of the technology was fully integrated into an established monitoring-based commissioning process, that technology, that outputs of things like the fault diagnostic software were integrated with CMMS systems in order to trigger work order requests, and to see that the results and findings from the tools were being regularly incorporated into the meetings conducted by the O&M staff or energy and facilities management. We saw real power from those who were able to leverage the technology findings to maintain ongoing support from higher level management to make energy waste visible. And that was coupled with the creation of public dashboards to raise awareness of energy use amongst the occupants of the building. The other best practice that we saw was the importance of deploying the technology for use in newly constructed as well as existing buildings. Those newly constructed buildings often not getting the appropriate level of initial commissioning and a full shakedown of systems. The analytics and diagnostic technologies can support doing that, and often one can see material savings right out of the gate from a newly occupied building. A couple of comments on product trends. It used to be that we saw a strong separation in terms of product offerings between the meter analysis tools and the HVAC system level diagnostic tools. Those capabilities certainly complement one another and we're beginning to see some convergence where they are offered in single software products. Anytime you talk about portfolio scale diagnostics across many buildings, hundreds of pieces of equipment, it's important the kind of summative and prioritization views that are being offered. And we're seeing that providers are giving that capability in a more elegant way and more commonly in the tools that are available. This is really a thriving technology space. There's hundreds of offerings on the market. That's growing. The predictive HVAC optimization technologies are much newer. They represent a smaller fraction of the overall landscape. The remaining capabilities across meter analytics and fault diagnostics constantly growing with new entrants to the market. The final trend that I'll comment on is that of the role of machine learning. We're seeing that that's being incorporated into the products in a couple of ways. First, to support data tagging, labeling, and interpretation during the configuration and provisioning phase. Second, we see it used in load predictions. And that might be tied into control optimization strategies and policies, or to things like savings tracking over time. I've given you some of the high-level highlights of what is the state of the technology, how is it being used, and to what effect, with what required level of investment and savings on the back end. This work is published at our website, smartenergyanalytics.org. You can find a final report of findings. We complement that with an applications showcase that highlights best practices across our cohort of users and a value proposition business case one-pager. So having talked about what's available today and how it's being used, I wanted to be sure to give some highlights from earlier stage R&D that we're pursuing to expand the capabilities of today's technology. Here we're really motivated by advances in public data availability, advances in sensor technology, falling costs, bringing about new information sources. We can use these to better understand building characteristics, building assets, And of course, we're always interested in building specific efficiency measures. So a bit more of what I'm talking about, and I'll focus your attention kind of at the 12 to 7 o'clock positions on this diagram. We're accustomed to using meter data, control system data, and weather data. Now we're interested in what additional information can be gathered from things like RGB and thermal images, from either street level orientations, aerial and satellite images, or even LiDAR, and how we can fuse across these sources to extract better understanding of building typology and characteristics and those efficiency opportunities. So what I'd like to share is work specifically around drone-based acquisition of thermal and RGB images. Cameras and drone hardware far less expensive than they were 5 and 10 years ago. We've also got a lot of advances in machine learning, computer vision, and image analysis. And I'll share how we're applying these techniques to auto-generate 3D building geometries, to extract exterior features. I'll focus on windows, but we could also imagine identifying photovoltaics and rooftop packaged units. And also identification of thermal anomalies. This is critical because everything I showed you on the analytics side so far was really absent of the thermal dimension because we just don't have that information available at scale today for most of our buildings. So starting with auto generation of 3D geometry, the first thing we do is take a building of interest and plan our drone flight. The flight then that we take is often overlapping circles over the building where we're constantly snapping pictures. We build up a library of 2D RGB images. From there, we apply off-the-shelf photogrammetry software that builds for us a 3D reconstruction from those 2D images, along with a lot of associated metadata. The R&D comes into play when we start then applying, line transformation and polygonization algorithms to extract the building footprint and the associated heights at each point along the building structure. From that point, we can then merge the information and generate a 3D model of the building in GeoJSON format for easy ingestion into other analytical packages. What's compelling about this is it shows promise to actually be scalable. It takes about 2 hours to do the flyover and image capture over a medium-sized building. Then, depending on your computational power, about a day to then post-process the data and spit out that auto-created 3D GeoJSON model. Next, I'll step you through how we're extracting exterior features from the building. I will talk about window to wall ratio. That's a very important driver of building energy consumption and loads, a key input to simulation tools that may be under the hood of many of the analytics packages that are available today. This is an important parameter that nonetheless is rarely known in the same way that like square footage is for existing buildings. So we begin again with our collection of 2D RGB images. We then apply a trained neural network deep reinforcement learning model to be able to understand which pixels in that image correspond to the windows on the building. That is then represented here in what we call prediction windows or MES, is a binary representation of each of the pixels that correspond to the windows in the 2D image. From that point, we then need to understand the 3D dimension in order to figure out where the windows lie on each facade in the building. So we bring in our 3D building model that I showed you previously, and we associate each of the 2D pixels with a 3D pixel. At that stage, we can then understand where each of those windows in our masks lie on the actual walls in the sort of Z dimension. And then we're off to the races. We do some triangulation, project back into 3D. And at that point, we have all of the geometric and volumetric information that's needed to compute that window to wall ratio, critical input to understanding energy flows and building energy performance. Step 3, understanding something about the thermal profiles of the building and what thermal anomalies may exist. Here we are doing the same kind of data capture. We're flying circles around the tops of the, above the building. But now we're collecting both RGB as well as thermal images in the 2D representation. The RGB is shown on top here in the slide, and the thermal is shown in grayscale right below it. We're going to reapply the same 3D reconstruction that we used to create the 3D geometry, but we're going to do that for both the RGB as well as the thermal representation. We can then understand from the 2D thermal images which pixels actually correspond to the building and which are all the surrounding stuff like pavement, trees, etc. The same masks can be created to extract then the anomalous pixels out of the 2D thermal image, and we do that through k-means clustering and some morphological operations. Once we have them, and that's shown in this black and red image here, we can superimpose them back onto the thermal image for further investigation by an analyst. We've now opened up the set of analyses that we can apply that introduce the whole thermal side of the equation beyond, mechanical system operations. So that's a little bit of a peek behind the curtain. We're continuing this work, exploring how we can auto-create 3D geometries without drone-based image acquisition by fusing aerial images with LiDAR representations. We're field testing these techniques to understand what actually is the value of that new information that we're creating. And I think really important when you think about the R&D and educational components of this work is that we've released it all as open source. We have tuned deep learning model architectures, and very critically, we've also released some of the labeled training data sets that are necessary to further extend these techniques, improve upon the existing tuned algorithms. That's really not something that you can readily access in the typical sense, and it's a huge barrier to actually being able to deploy and develop these kinds of techniques. I'll conclude with just a couple key takeaways to leave you with. Remote analytics, smart building technologies are available today. They're enabling deep savings cost effectively. They're also introducing a real streamlining of operational processes. There's additional promise to advance the technology even further through some of these kinds of new data sources that I've highlighted today, and the feature extraction and data fusion techniques that I presented. We always our starting orientation for much of our work is around efficiency measures. How can we identify them? How can we implement them? But I do want to note that there's a lot of additional directions that this work could take, and other applications to which I think it could be really applied, whether that's additional kinds of outdoor asset identification, maybe it's siting or tracking distributed energy resources. If you think on the planning side of things and the hardscape, things like cool surfaces and understanding vegetation ratios, water bodies, or back to the buildings and being able to establish localized inventories of building typologies across the stock for a more detailed understanding that can inform the planning of programs or targeting the delivery of programs. With that, I'll conclude my prepared remarks. Thank you for your attention and open it up to any questions from the attendees.
Thank you, Jessica. And I think we have quite a large number of participants, and I'm sure you'd hear a lot of applause if that came through. We don't have the canned applause to come through. So you've got a couple of, somebody sent a message, clap, clap. So there you go.
Thank you.
So, excuse me, hang on. The first question that we have is related to energy savings. And the concern is that the data that you presented was data that happened before the pandemic. So it was when we were occupying the offices, and most of our energy use during the day was in an office setting. So the question is, do you see any big modifications on these numbers because of the need to ventilate and clean the air in many buildings, such as hospitals, schools, hotels, offices, and so forth?
Mm-hmm. Yeah, that's a great question. So it's correct that we shared results that were kind of energy savings, before and after installation of analytics and diagnostics in the previous normal case of how we occupy and operate our buildings. I will note that not all of them were offices. We did have, other representation of other building types from different commercial subsectors. Nonetheless, the question is still relevant and germane. I would say that yes, some of the strategies and recommendations that have been discussed for increasing ventilation of our buildings and different levels of filtration and so on do have non-neutral energy impacts. That is a fact. What I would like to highlight, however, is that there's a couple of ways that the fault diagnostics and energy analytics tools can very much support maximizing efficiency and effective operations in the new normal case. So first is that we kind of know that when our buildings are under occupied, we are not necessarily that great at turning them down and setting them back. These technologies can very much bring those insights to light and bring visibility to the fact that you're not shutting down as far as you think you are. In the case of reoccupying, there's also a lot of value in the diagnostics to be able to continuously run and provide feedback that you are indeed conditioning your building according to those new healthier policies that you think you have implemented in the controls.
Great. Thank you. Thank you, Jessica. We now have even more questions for you to answer. One question is there a possibility of using AI or machine learning to allow operators to guide the basic outcomes, such as cost reduction, carbon reduction, and let the software manage the minutia?
Yeah, there's two. I'll tell you how that's currently done. I talked a little bit about those newest in the pack predictive optimization technologies, focused on the HVAC systems. So those actually are doing a multi-objective optimization across considerations like total cost of energy, usually not sacrificing occupant comfort. And in certain cases, maybe they're looking at, if you want to provide grid services, whole building demand at certain times a day, things like that. So in that respect, the balancing of those objectives can be delivered in an automated fashion without requiring the operator or manager to get into the minutia. I think that's just barely scratching the surface. So I think there's tremendous opportunity to explore, say, feedback from the operator. You could imagine whatever the analogies are to, hey Google, yesterday was a little stuffy in here. See if you can improve. Kind of bringing user and operator feedback into the loop, kind of as an additional, human as a sensor kind of paradigm. That could be really fun to explore. So I think there's a long way to go. And I hope I answered your question about the ways in which that's delivered today, to illustrate basically what the opportunities may be going forward.
And it's kind of a feedback loop, right? That you
Yeah.
start with something, see if it's used, and then it builds on itself depending on what proves useful.
Right.
The next question is a question from someone at the lab, actually. Utilities often offer free pared down energy information systems programs to their C&I customers. Are these programs, were these excluded from the study?
Let's see how to answer that. I'm not sure exactly what the person asking this question has in mind when they say pared down EIS programs. What I'm familiar with is that large customers can get, access to, many times a kind of bare bones. Here's your interval meter data. What we are working towards with a lot of these results is providing a very comprehensive evidence base for the savings that can be obtained through installing these technologies and using them, of course, and the cost of doing so, in order that we can motivate further incorporation into utility programs in a more formalized way beyond, oh, you can look at your data through this portal if you want to.
Okay, great. Thank you. We have one last question, and you have 3 minutes to answer. Or 3 or 4 minutes. To do this drone-based, and if anybody wants to ask additional questions, please do. To do this drone-based diagnostics of buildings, are there currently any companies that are offering this service directly, or is there a chance for a municipality to participate in a pilot program?
This is all very new. There are companies offering components of what I shared today. But as far as putting all the pieces together, so what is available today, you can buy drones, you can buy cameras, you can, in some limited cases, acquire pre-existing images to train and tune learning algorithms against, although we did not find that sufficient for our purposes. We had to do a lot of that ourselves. So you can get those things. When it comes to finding the, say, neural network architectures, those are in the literature, but there's a very heavy lift to implement them, tune them, and package them for these specific applications. So in making that available, we hope to inspire ongoing adaptation and improvement of what we've done. There are companies who will sell you images, but none that I know that are, offering, we'll fly a drone and give you 3D building geometries and, detect all the thermal anomalies on your buildings and extract, not quite in that way. Municipalities and piloting, if there are specific folks in attendance who are interested in trialing some of these methods, I welcome you to contact me, please, and my contact information is on this slide.
And I would imagine if there's any companies that are interested in getting something started, they could contact you as well, or
Certainly,
utilities, or anybody that wants to tap into your expertise, right?
absolutely.
All right, well, thank you very much, Jessica. We really appreciate it. There's been great interest in your presentation, and thank you again for supporting the Best Center in this by
It's my
another great
pleasure.
presentation.
Yes, thank you for having me. Bye, guys.